Okay, so I want to continue the historical survey. It is amazing to me how much changed in science in those rapid decades after the turn to the 20th century. When the 20th century started, the atom, this little thing called the atom, was the most fundamental part of nature. And everything changed through a series of discoveries that I'm starting to tell you about. And a series of discoveries that had profound effect on science, on industry, on war. I'll tell you something about World War I. The new discoveries in science that had a profound effect on, gee whiz, mustard gas killed a million people in World War I, on various other things going on in the world. And of course, then, as the scientific discoveries continued, by the time World War II came around, we knew enough about the nucleus, about the neutron, about nuclear fission, that resulted in the development of the atomic bomb. Last time we were talking about Marie Curie, one of the great scientists in the history of the world. She was Polish, Maria Sklodowska, from a family that was well-to-do in Warsaw, but which lost their fortune because her parents got mixed up in the drive to make Poland independent of Russia, which has been something Poland's had to work on many times in their existence. And so she then, her older sister, went to Paris to study medicine, and finally she scraped enough money. She had a heartbreak along the way, romantic heartbreak, and she went to Paris and studied physics at the Sorbonne, with really living on the edge of financial bankruptcy. She met Pierre Curie, married Pierre Curie, and they did a lot of experiments together in Paris. He was a professor of physics at the University of Paris. She couldn't be that because she was a woman, but together they worked very well. Oh, here comes Ray. Welcome, Ray. They were working together on this mysterious radiation coming from certain minerals. And this was one of the new things. Röntgen discovered X-rays in 1896 in Germany. Becquerel discovered radioactivity along with the Curies around that same time. So from Becquerel's work, you knew that something was giving off radiation, giving off emanations independent of fluorescence when you shine light on it. And that's what the Curies were pursuing. What was it in pitch blende, in torgonite? What was it that was giving off some emanations independent of being in sunlight or some internal source of energy? That's what they worked on. They did heroic work, starting with tons of pitch blende, doing repeated chemical separations until they succeeded in finding out two elements that gave off its own emanations, its own radiation. Didn't know what that radiation was, didn't know the physics of it, didn't know the nature of it, but they could tell with this electrometer, this instrument whereby the emanations would then ionize the air around the glass tube where the material was held. They could sort of measure the quantity of radiation given off. And that resulted then in, first, the discovery of element 84, polonium. They published in 1898 in April, July. And then a little bit later, separation of radium, element 88, that produced this radiation. And so, by the way, element 96 later on was named in honor of Marie Curie. So that was really a crucial step in science. And Marie Curie was a well-known person. She was the first woman to win a Nobel Prize. She was the first person to win a Nobel Prize in two fields, one in physics, one in chemistry. She won the first Nobel Prize with Becquerel and her husband for the discovery of radioactivity. She won her second Nobel Prize for the discovery of these elements. And so she's the only person to win Nobel Prizes in multiple sciences. Very well recognized person. She was entombed when she died in the Pantheon in Paris, the first woman to be so honored. She had a hard life, of course. She wanted to go back to Poland to work, but the University of Krakow wouldn't give her a faculty position because she was a woman. She married Pierre Curie, but then he died of a carriage accident in 1906. Only after that, I mean, she'd won a Nobel Prize by this time, did the University of Paris allow her to succeed her husband as a professor of physics at the University of Paris. Only after she threatened to leave did they saw her as the first woman to have a professorship at the University of Paris. By the way, there were scandals involved too, public scandals. After Pierre was killed, somewhat later, she had an affair, a romantic affair with Paul Langemann, who was a student of her husband's. And that became a scandal in Paris. Tabloids, papers got a hold of it. And then when she was up for election to the French Academy of Sciences, that was used against her to show that even though a smart scientist, she was not deserving of being in the French Academy of Sciences. Also, there were rumors circulated that she was Jewish and an atheist. But yeah, she was an atheist. I explained earlier that her father was an atheist, her mother a devout Catholic. So she was an agnostic through her life. But to discredit her, people circulated rumors that she was Jewish and an atheist. What a bad combination. In France in 1906, 10 or whatever. So she was not elected to the French Academy of Sciences, even though she had won a Nobel Prize. And it was actually one of her students that finally was the first woman elected to the French Academy of Sciences. So she won a Nobel Prize in chemistry and in physics. It was her student, Irene Perret, who became the first woman elected to the French Academy of Sciences in '62. She built the Radium Institute. That's why she didn't leave France. She had multiple opportunities to go back to Poland later after she won one or two Nobel Prizes, but she chose not to because she wanted to build an institute in Paris dedicated to the study of radiation, its uses, physics of it, its uses, and what good it could do for mankind. And then her daughter, she had two daughters, Eve and Irene. Irene became a Nobel laureate. Irene married Frederick Joliot, and they worked together at the Radium Institute. We'll come back to this, but they won the Nobel Prize in 1935 for the first artificial production of a radioisotope in a certain bombardment of aluminum with an alpha particle. So a very distinguished family. The unit of radioactivity is named after Marie Curie. And element 96 is named after her. So one of the great scientists in the history of the world. And that tradition in France, my field is nuclear physics. And I've had many colleagues, nuclear physics colleagues from France, and a lot of them are women. And that Marie Curie tradition continues to this day in France, where a smart young female student wants to be a scientist, a physicist, following the lead of Marie Curie. So Marie Curie discovered two elements with her husband, figured out that there was this thing called radioactivity, but not much else was known about it. Along about that same time came Ernst Rutherford. He was from New Zealand. He was a smart son of a farming family, Brits who immigrated to Australia or New Zealand for opportunity. And he was a smart kid, and he then got a chance to go to Cambridge University to get his graduate work in physics. And he worked under J.J. Thomson. I told you that story. J.J. Thomson's the guy that discovered the electron. And so the young Rutherford had the chance to go work in that famous laboratory of J.J. Thomson in Cambridge. He got his degree. He did well. He got a faculty position in Canada at McGill University. A rich tobacco industrialist in Canada decided that he would establish a scientific institute in Montreal, McGill University. And Rutherford was brought over as a young, rather well-known physicist already to set up that laboratory studying nuclear physics, although that wasn't the term yet. So he worked at McGill University for a while. And there he worked on understanding what is that internal radiation being given off by these things like polonium and radium and the minerals in which they were found. And he did experiments, realized there are different kinds of radiation. And for this, he won a Nobel Prize for his understanding that, yeah, some of the radiation given off are alpha rays, he called them, alpha, beta, gamma, the Greek letters. That these alpha rays were charged particles, and they were heavier than electrons, but not very penetrating. So in this schematic thing, if you have alpha particles, a view of alpha particles, they can stop in your hand, not going to penetrate in your hand. Of course, we know now all about alpha radiation. It's used a lot for medical purposes, put in radioisotope to kill cells. They don't penetrate far, but they drop their energy in a very sudden and effective manner. And then Rutherford also realized that there's another kind of radiation that are slightly more penetrating. Beta rays, he called them. They're actually electrons being emitted from this internally active substance, polonium or radium, uranium or whatever. And then he found also that even more penetrating were gamma rays that could penetrate the hand, a piece of aluminum, a piece of lead, if they're higher enough energy. And those are similar to, but higher energy than what I should have said Röntgen. That's a mistake. Becquerel discovered radioactivity. It was Wilhelm Röntgen that discovered X-rays in Germany. So it was Rutherford that first proposed that this radiation actually comes in three forms, alpha, beta, and gamma, that now we know well. And for that, he got the Nobel Prize. And he worked with a young guy named Frederick Soddy on understanding the nature by which radioactivity occurs. And they were the first to realize that there's a half-life, that every radioactive material that emits alpha, beta, or gamma radiation, they started to realize, could be characterized by a half-life. In other words, how long it takes that thing, that element, that isotope we know now, to lose some of that energy. And the half-life was a key part. That's the spontaneous process. And it means that half of those atoms that is radioactive decay, lose their radioactivity, half of them in that time, we call a half-life. And that's a statistical process. And so he was the first to point that out, that a radioactive decay could be characterized by a half-life in this statistical process. and a plot of activity versus time, say, the logarithmic decay. Well, and what that means is that, if you start with a certain number of radioactive species at this time, that in one half-life, you've lost half of them. Another half-life, you lose another half. Another half-life, another half. And so you never get to zero, but you approach it in an exponential way, losing half the species every time loses energy and decays to an adjacent element or isotope. And so there's no memory involved. That's the point. That there's no memory involved. Every time, at every point in time, there's no memory of how many things have changed their nature, done radioactive decay before. And so it's a very statistical process. And so that key understanding was part of the Nobel Prize that Rutherford won, I think in 1908. Rutherford then, after his success, was called back to Manchester. He went to Manchester to assume a chair of physics. So he went back to England. He then started doing experiments on understanding radioactivity and such. He had already, in his experiments in Montreal, realized that these alpha particles, one type of radiation emitted, were actually helium atoms, ionized helium atoms. And so he did, therefore, some experiments with Geiger, famous Geiger counter, Geiger and Marsden, to look at, which we do, scattering alpha particles coming from these radioactive species off of foils, off of elements. You see, he had an idea earlier that there must be something else in an atom, some uncharged particle. And so he was pursuing these experiments, simple experiments, where you have a source of alpha particles, radium or polonium or something that was occurs naturally but has been separated out, or hitting foil and looking at the scattering of those alpha particles. And this is what, of course, somehow these PDF files sometimes don't transfer, but this is Rutherford. You can't see it very well. It's better on the original. He was a very good experimentalist. And you see, when J.J. Thomson, a decade earlier, had published the existence of electrons in an atom, electrons are small, negatively charged particles. And his assumption was they were like raisins, plum pudding, spread or distributed in a sea of positively charged material. You had a positive and negative charge that would balance each other. Atoms are neutral unless you do something to ionize them. So there were negative charges distributed in a continuous distribution of positively charged material. That was an atom. Well, he realized that wasn't right because of his famous experiment. The famous experiment was that they, and this is just a schematic, had alpha particles hitting a gold foil, a thin gold foil, and some of those alpha particles, those little helium nuclei, helium atoms, would scatter. They would deflect because of a collision with electrons. They might scatter, come close to this electron, they would scatter, change their direction a little bit. Here, this one would be close to this electron, and like doing pool, shooting pool, the other ball would scatter off of another one and deflect. Well, that was understandable. The shock of this experiment was that there were scattered alpha particles detected at large angles. that every once in a while, after particle came in, it got deflected backward to a large angle. The only way that could happen is if there's a very large mass right there. So a little electron here or there could not deflect because this projectile coming in is heavier. That's a helium atom. It's far heavier, it's thousands times heavier than the little electrons. So the only way to get a helium nucleus to backscatter would be as if there were a giant mass in the middle of the atom. And that was the shock of Rutherford's experiment. And he said that this finding was as incredible as if you fired a 16-inch cannon shell at a piece of tissue paper and came back and hit you. So this was unimaginable that this could happen because the electron is small, the projectile, the helium, would be at least 1,800 times bigger, more massive. The atom is mostly empty space, so how could you get something scattered backwards? And that was the shock of that experiment. When he published that, it produced a wildfire of activity and thought and argument. And his conclusion then, there must exist a nucleus, he called it. There must exist a center part of the atom that it has almost the whole mass of the atom in one little spot. So J.J. Thomson's plum-pudding model was wrong. Somehow there was a nucleus surrounded by electrons in an atom. And so we're getting closer to this idea that there are nuclei. Rutherford is viewed as one of the great scientists in the history of the world and certainly of the United Kingdom. When he died rather prematurely at age 66 in 1937, he was buried in Westminster Abbey, right next to the body of Isaac Newton. So that really shows that Rutherford was a great scientist in the history of the world of the United Kingdom. Element 104, by the way, found much later, of course, is named in his honor, Rutherfordium. Well, now we know that the atom is mostly empty space. Now we know that most of the mass is right in the middle. For example, helium, now we know that a helium nucleus has 2 protons and 2 neutrons. We know that each of those has a radius of 0.8 Fermi. Fermi is 10 to the minus 15th meters, so very, very small. So that's a Fermi. That's nuclear scale. That's about the size of the helium nucleus. The atom, helium atom, is an angstrom across. Actually, another small measure, an angstrom is 100,000 Fermis. And we used to think that an atom was like a solar system. It is in some ways like a solar system. You've got, of course, got the sun, got planets orbiting around the sun. And we should scan out a bit. And of course, we understand solar systems. All the motion solar system, of course, is counterclockwise. It's the way that cloud of gas was rotating when the sun formed. Most of the mass went into the center to form a sun that continues to rotate this way. Leftover material form planets. And of course, here, it's the electrical, the gravitational force. That holds the planets in orbit around the sun. The gravitational force is attractive. It's never repulsive, it's only attractive. And we used to think that that was the model here, but it's a little more complicated than that. So now we view that neutral helium would have 2 electrons moving around the nucleus, but you can never say it's here or here. You view it as a cloud, a distribution of probability where the electron could be somewhere at any one time. You never know for sure. The point is that the atom is mostly empty space. The atom is 100,000 times bigger than the nucleus. And so that's where all the mass is, in this small little nucleus. That we understand now. But it wasn't so clear, of course, in the days of Rutherford. In this historical progression, a guy named Moseley came along. He was British. He came to Montreal initially, then he came to Manchester. Now, maybe he was never in Montreal. He came to Manchester to work with Rutherford after Rutherford went back to England from Canada, and he worked on X-rays being emitted by different elements, and he figured out that there's a relationship. If he worked out a relationship, there's a systematic relationship between the wavelength of the X-rays emitted by hydrogen or helium or tin or copper or every element and the atomic number. And so this was about, this is a fingerprint. Well, yeah, the chemistry of tin is different than the chemistry of helium. In addition to that, the difference is apparent from the X-rays emitted by these atoms. And that's what Moseley worked out. And in the process of working this out, he realized that there were some gaps that he then could predict by knowing this relationship, that there should be elements with, you know, hydrogen is element number 1, helium 2, lithium 3, beryllium 4, so on, that the atomic numbers 43, 61, 72, and 75 were missing. And so he was able to predict that there should be elements there. And they were discovered, technetium, promethium, later on hafnium, rhenium, by his predictions, by the Moseley law. So he made a big contribution. He didn't live long. World War I broke out, the Great War, and he enlisted in 1914. And he didn't make it through that. He was in the communication corps. He was on the front line at Gallipoli and in Turkey. And while he was trying to make a telephone call to the people back from the front line, he was killed by a sniper. And so he died very young, I think age 27. Yes, age 27 by a sniper who was in the Great War. He died in 1914. That was a huge loss. Isaac Asimov said that this may have been the greatest loss, greatest single loss of a person in all of World War I, among all those people killed in that gruesome war. As a result of that, the British government, after Moseley was killed, did not allow scientists, for example, to enlist for combat. They could be used in a war effort, but not to go to the front line and fight. So Moseley accomplished a lot in this short period of work. And so you see, this is the periodic table as it was in 1935, 20 years after Moseley did his work, but you can see his point, predicted that there should be here, and there should be element here. And they were found. By 1935, the other two, hafnium and rhenium, had been found. Hafnium is here, rhenium is here. So those were 4 holes in the periodic chart that he was able to predict. World War I, a terrible war, started in 1914. And scientists were pulled into that war effort, as also World War II. This is more through chemistry. This is an interesting person, Weizmann. Chaim Weizmann, who was a Russian Jew, Jewish family, 15 kids, grew up in Russia, left Russia, came to Germany, did his PhD work in Germany before World War I, biochemistry. He went to Manchester, he heard about Rutherford. He went to Manchester to work with Rutherford. Weizmann also was a ardent Zionist, lobbying for, working toward the creation of a Jewish state at some point for the Jewish people. He was a biochemist. He was looking for an organism. He found an organism that could decompose starch. He hoped to use that to make synthetic rubber. The rubber had been discovered. Rubber was important for industrial purposes for the war effort. But to make that synthetically would be a great breakthrough at that time. Well, that didn't work. But in the process, he figured out a way to make acetone. This is acetone. And acetone was important to England at that time. At the beginning of the Great War, you know, England had a tremendous navy. They had these huge cannons on ships. But as a propellant to fire the shells, these huge shells and these big cannons, you needed acetone. It's part of the, is that right, Mark? You understand the chemistry of that. You need acetone to make that explosion, right?
I didn't know that.
Oh, geez. Found something that Kevin didn't know. That's good. Maybe a physicist, maybe Phil King or Sharon King know that.
One thing I use acetone for is stuff.
Right.
Clean glue all, yeah.
So acetone was important as a propellant, part of the propellant, to fire up these big shells from these huge cannons on British ships in World War I. They were in short supply of it. Couldn't make it in a conventional way. And Weizmann was an entrepreneur. He happened to know Lord George, who became then Prime Minister in England in this period. He also went to meet Churchill. Churchill was the first Lord of the Admiralty, head of the Navy in England at this time, and said, you know, maybe I can, and because there was a call issued to the UK, to England, we need help on this acetone problem. And Weizmann saw that, realized that his discovery of a way to break down starch could be used to make acetone. You can make acetone in small milligram quantities in his laboratory. He went to see Churchill, and Churchill needed tons of acetone. And so Weizmann was a real entrepreneur, and Churchill gave him unlimited resources. Here, go back to your lab, scale this up, and come to our aid. And it worked. After 2 years of hard work in his laboratory in London, Weizmann showed that he could scale this up to make acetone on the ton scale, which saved the Navy in England in World War I. They asked him after the war, what can we do? How can we reward you, Dr. Weizmann? And his answer was, help me find a land for the Jewish state. And so that promise by the leader of England after World War I resulted eventually in the formation of Israel in 1949. There were a lot of twists and turns, but there was that Weizmann, he accepted that pledge after he saved their butts on acetone, and that led some way to the formation of Israel 30 years later. And he was the first president of the state of Israel. Of course, he knew Einstein. Einstein was also a fervent Zionist. And he and Einstein worked together to form a Jewish. And Einstein could have gone to be the president of Israel too, but he didn't want to do that. Did you ever heard that story, Ray?
I have not thoroughly enjoyed it. So So this idea of the state official came up way before it. So what you're saying?
This what? Oh, idea of a state.
Of the state.
Oh, yeah, sure. People have been working on this in the early 1900s, right, Mary?
Yeah.
Yeah, yeah, right. And Weizmann took this idea to Lord George, then Prime Minister Lloyd George, saying the place is Palestine. They had talked about somebody, the leaders in England proposed somewhere in Africa. Where was it? Ghana or somewhere. I'm not sure, as a place for the Jewish state.
Also South America.
South America. Why South America? Just because of the number of Jews and stuff, yeah, a place. Right. Right, that's right. But Palestine, of course, had a history of the Jewish peoples, and that's the idea that Weizmann took to Prime Minister Lloyd George and won him over by saying, yeah, Palestine is kind of a rocky, barren place, but it's much like your Wales, but that's where Lloyd George came from, was Wales. And so that brought favor also. And another use of science, for better or for worse, in World War I was chemical weapons. Otto Hahn was a German chemist. We'll come back to Otto Hahn many times over, a great German chemist. He got a Nobel Prize in 1945, I believe. He did the seminal experiment we'll come back to in December of 1938. He and Fritz Strassmann did the seminal experiment to prove that when you hit uranium with neutrons, it breaks into two pieces. And that very rapidly led to the idea of making atomic bombs, Manhattan Project, and so on. That was later. This time, Otto Hahn was a young chemist, well-renowned chemist. He came to Manchester to work with Rutherford. He also worked with him and McGill. And he became the father of radiochemistry, nuclear chemistry. He was a chemist. He was also a lieutenant in the German army when World War I broke out. And since he was such a chemist, you see, you got to understand the background. Kaiser Wilhelm II came to Berlin in 1910 to establish what we now call the Kaiser Wilhelm Institute, now called Max Planck Institute. At that time, Kaiser Wilhelm started that. And so Kaiser Wilhelm, the head of Germany then, supported a scientific laboratory. Now, part of it was applied, they had people dying in coal mines from explosions, not understanding the volatility of coal gas, methane. And so Kaiser Wilhelm then set up this laboratory, these Wilhelm Institutes in Berlin, around Germany. And Otto Hahn was part of that. When World War I started, he enlisted, or he bought into the German army, and they helped put chlorine in shells, beginning of chemical warfare. Fritz Haber was a well-known German chemist who was also in part of the war effort, and he helped really, along with Hahn, but more senior than Hahn, developing gas warfare. And so, of course, before World War I, Germany had the most robust chemical industry in the world, doing various industrial chemical processes to help humanity and the states and sell products. But they also developed phosgene for the war effort, carbonyl chloride. It's a It was the next step after chlorine. Yeah, you could put chlorine in shells to kill people effectively, but even better was this compound chlorine, phosgene, that was a big step forward. And the next step after that was mustard gas, another form of chlorine, dichlorethyl sulfide, even worse. So that was really a big part of World War I, these chemical weapons developed by these German scientists. Mustard gas was effective. You could have gas masks that would help troops survive being bombarded with chlorine gas or phosgene, but mustard gas would dissolve the rubber around the gas mask, and so there was no protection against it then. And so it caused a lot of casualties, maybe a million of the 29 people that died in World War I was due to chemical weapons. And so Otto Hahn worked in that. You know, it was a national emergency. We can debate that, the ethics of that, but that was a national emergency in Germany, and so it was part of that effort. Later on, of course, he did great things in science. He and Lisa Meitner, who we'll come back to, the Austrian lady, also Jewish, they discovered L-91 for titanium later on in after World War I. So that Weizmann and Hahn are two examples where science was pulled into World War I needs. Then Niels Bohr, Danish physicist. I have a lot of connections with this name because I've spent 3 years of my life at the Niels Bohr Institute in Copenhagen. His legacy was prolonged by he established it, an Institute for Nuclear Physics as part of the University of Copenhagen. That's where I've spent a significant part of my career. Niels Bohr came to work with Rutherford in Manchester in 1912. I mean, the status was that Rutherford figured out that there's a nucleus in the atom. So an atom is composed somehow of a positively charged nucleus, like the sun. Electrons in some kind of orbit around the nucleus, like planets. But this didn't work by classical physics. It works for macroscopic systems like planets and stars, basically because the gravitational force is only attractive. But for the atom, you've got the nucleus, you've got electrons. Instead of gravitational force, the force is the electrical force. The gravitational force is only attractive but the electrical force can be attractive or repulsive. Because the nucleus has positive charge, the electrons have negative charge. So it's the electrical force that keeps the electrons in orbit around the nucleus, but it's not stable. For several reasons. One reason is that then there's electrical repulsion between the electrons. Two electrons have a negative charge. Yes, the attraction to the nucleus is keeping them in orbit, you might say, but the repulsion of like charges, unlike charges attract, like charges repel, that makes the nucleus, the atom, unstable by classical physics. And so a solar system model of the atom does not work. People understood this. People debated this. Bohr was Danish, athletic guy, smart guy. His father was a physician and on the medical school faculty at the University of Copenhagen. But how do you redo the laws of classical physics to explain the stability of atoms, for example? Bohr came to work with Ruth for 4 months. Bohr was a terrible experimentalist. They wouldn't even let him in the lab because he would break things. But he was a very smart guy on the theory, on the mathematics, the theory of physics. It led to the realization that orbits of electrons are quantized. I'd like to tell you about what that means. He won the Nobel Prize in 1922. Element 107 is named after Niels Bohr, a Danish physicist. I just want to show you, this is how the periodic chart looks now. Everything's been filled in. But you see, the Bohr, it's named after Bohr. 107, 104 named after Rutherford. Who else? 109, we'll talk about Lisa Meitner, named after Meitner. Oh, here's named after Röntgen, Wilhelm Röntgen, 111. Who else do you know? Einstein, element 99. Curie, named after Marie Curie, 96. So on and so forth. Oh, by the way, now, this one. Who's that name? What's that name? Tennessee. So this is, see, there's elements named after Berkeley. There's an element named after the state of California, 98. That's Fermi. We'll talk about Fermi. Named after Lawrence from Berkeley. We'll talk about him. But the most recent two were done in experiments in which Oak Ridge was deeply involved, also UT. And so element 117 is named after the state of Tennessee. Tennessee. It's a halogen, so it's fluorine, chlorine, bromine, iodine, astatine, Tennessee. That's why it ends in INE rather than something else. Anyway, how did Bohr solve this problem of the stability of the atom? It doesn't work by classical physics. And so he realized we got to throw classical physics out. You know, another thing too, what's wrong with this is people do by the time, if you accelerate electrons and to keep it in a certain orbit, it has to be accelerated. It will radiate energy. An accelerating electron radiates. So that's the problem. See, planets in the stationary orbit around the sun don't radiate, don't lose their energy. It's a stable orbit. But an electron in a circular orbit has to be accelerated to stay in that circular orbit. It will then radiate. You know, that's how we have accelerators now. Light sources. That's how light sources work in big accelerators. Accelerated electron radiates different wavelengths of radiation. And that also makes, that's the primary reason that the atom is unstable by classical physics. Bohr's solution is to say, when an electron is in a stable orbit, it doesn't radiate. That energy is conserved. An electron is in this state, in this orbit or this orbit. It's in this orbit or this orbit, it does not radiate. And the only emission radiation occurs when an electron jumps from this orbit to this orbit. And the radiation is then proportional to the energy difference of those two orbits. So that's quantum physics. So he invented the idea of stationary orbits where electrons don't radiate when they're at this energy level, this one, whatever. And that then you can elevate it into different orbits. Orbits that are specialized and depend upon the nucleus. So there's a certain number of orbits and energy levels for a hydrogen atom, different ones for helium atom, for neon, and so forth. That was the Bohr model of the atom, that you have quantized orbits. Only certain radii of the orbits can exist in the quantum mechanic view of the atom. I'm not expecting you to catch all this. I'm just doing a quick overview. But related to this is Planck's discovery. And so there's the Planck constant that we hear about. Max Planck was a great German physicist. And you know, when you heat the burner on your stove, it turns red. If you have electric heating element, and it radiates. It radiates heat. It radiates red light, but it radiates more than that. It's called a black body radiator. If you heat the perfect body and let it radiate without any interference, it will send off radiation with a certain distribution at a variety of wavelengths or frequencies. Gotta move this here. And this is what Planck figured out in 1900. This is the spectrum of radiation from a very hot object in the perfect world. A little bit of intensity is at low frequencies. It increases in intensity until there's a peak. That peak is related to the temperature of that hot object. That's how we tell the temperature of stars, by the way. You know, there's red stars that are pretty hot, but when you look out into the sky and use your instruments, there are stars that are more blue that are hotter. That's how we tell the surface temperature of stars, by the wavelength of the peak radiation. And classical physics had a problem in the ultraviolet frequencies. Why does this fall off sharply? Why does it keep going? More and more radiation at higher and higher frequencies. Well, Planck solved that by saying that the frequencies emitted are quantized once again. And there's a Planck's constant, H, a small number, but a fundamentally important number, where the energy of the radiation emitted is that small number times the frequency. And so that's Planck's constant. It helps describe the distribution of radiation from a hot object like a star. This comes up in Einstein's famous experiment in 1905. I haven't talked about Einstein, but in this active period, early 1900s, before World War I, Einstein proposed in 1905 the photoelectric effect. Won a Nobel Prize for this in 1921. And element something, the name of Einstein, which element? 90. I just had that. Einsteinium. 99. Einsteinium. Oh shit, I'm going the wrong way. Sometimes I don't do this right. So Einstein solved another puzzle, that when you shine radiation onto a metal surface, it gives off electrons. Electrons are emitted. And in 1902, it's observation that the energy of the emitted electrons, when light shines on a metal surface, increases with the frequency of the light shining on the metal. And classical theory said that the electron energy would be proportional, given off to the intensity of the shining radiation, not the frequency of the shining radiation. So that was a big problem. Einstein explained that in 1905 by going to the quantum realm, also saying that electrons coming off could be viewed as, or that the radiation coming in is viewed as the frequency multiplied by Planck's constant. So this was a key part of using Planck's constant. The energy of the photon is Planck's constant, small number, times the frequency. E is equal to h nu. And that helped Einstein explain the observation that the light coming in could be viewed as bundles of photons, packets of energy, not as waves. And that's the photoelectric effect. By the way, that's important. That's how solar cells work. Photovoltaic cells we use to make electricity now operate using the photoelectric effect, using semiconductors. Light from the sun shines on a semiconductor, electrons are emitted, run through a circuit. That's electricity that PV cells generate. And then to understand the other conundrum at this time, just know that light, like from a flashlight, has many frequencies, wavelengths. So you send light from a flashlight to a prism, a piece of glass manufactured this way, that the curvature through the prism depends upon the wavelength of the light. And that the smaller wavelength light, violet for example, bends more than the longer wavelength part of white light, red. And so, you see it all the time. Light goes to a piece of glass, through a prism, it's broken into a spectrum. A rainbow is like this. Light is scattered and dispersed off the back end of raindrops. When you have rain there and the sun's back of you, that's what a rainbow is. It's the same effect. So, and so that's what a spectroscope is. You take light, sent through a prism, you shine on the screen, and you have the component wavelengths of that light. Well, or you can then heat different gases, hydrogen gas, helium gas, and send it through a prism, and you see not a continuous spectrum like when you have a light bulb, but you see certain lines, red, green, blue. Well, that's important in astronomy. That's how you tell that the universe is expanding. I'll tell you about that in a minute. But those lines are important fingerprints of whether you're heating hydrogen gas or helium gas or neon gas. By understanding those fingerprints, those discrete lines, you know what's present in the atmospheres of stars. And indeed, here's hydrogen. When you heat hydrogen gas, you see this red line at that wavelength, and like a greenish one, and then ultraviolet ones. And sodium, sodium ones are yellow. Well, that's why, because the two dominant emissions when you heat sodium gas is two yellow lines. That's why sodium lamps are yellow. Helium, red, yellow, neon. So that's the fingerprint of the element. We know that experimentally. The problem was, how do you explain that? That was one of the conundrums when Bohr came along. What's your model of explaining the wavelengths of these emission lines when you heat hydrogen, sodium, helium? That was one of the big problems. And so his model of the atom had to address that. And what he did was say that electrons can be in this orbit or in this orbit, the ground state, lowest state, or an excited state, and that the light is emitted only when the electron drops from one orbit to another orbit. And the emission is proportional to the difference in energy of those two stationary orbits. So if you have an atom here, a nucleus, electron in this orbit, shine ultraviolet light on it, the electron gets bumped up to this orbit, absorbs that amount of energy, that photon, ultraviolet photon. It'll stay there for some time, microseconds or femtoseconds or seconds, and then it gives off, it radiates as it jumps back to a lower energy state. Well, that's how you get emission spectra. If this is hydrogen, one photon, then that is a very characteristic photon pulse of light emitted. Or you might have more energy coming in to bump it up two orbits. And then it might decay by an ultraviolet photon of that difference of energy, or it might have a two-step thing where it jumps to one and to the other. A visible photon, ultraviolet photon. So that's how you get different lines emitted by an atom of hydrogen or helium by the electrons being excited to different orbits and then jumping back down, emitting those characteristic fingerprint wavelengths. And so there was this thing called the Balmer series, the Lyman series, where for hydrogen, we have different orbits. For electrons, once again, when the electrons are in those orbits, they don't emit or radiate or absorb energy. But then when they can emit or radiate energy, only when they jump from one to the other. There's this line, Lyman series, there's an alpha, beta, gamma, delta. You have those sets of lines emitted, or you have the Balmer series, these transitions. And those are the fingerprints of hydrogen. And Bohr was able to explain that. A big victory for his atomic model. And by the way, when you look out into the sky, you look at stars or you look at interstellar media, nebulous, they're absorbing energy from, there's a star in the middle, radiating energy. The cloud around here absorbs that light. The electrons get bumped up to a higher orbit. They fall back down. The universe is mostly hydrogen. And so that right there, that red line of hydrogen, is the most common emission seen in the universe. And indeed, that's why this nebulous glows red when you look at it. It's emitting primarily that one line of red light. So then how do you know expansion of the universe? Which of you know that? How do you tell the universe is expanding? Anybody know? Bill.
The red light, even if you're exceeding, you don't have a Doppler effect. And so the red light will be a lot longer than it is in its
the train whistle effect. You hear the train approaching, and the sound Doppler shifts to a, which way? Lower, and the train passes you, and then it's receding. It shifts to a higher frequency. Well, that's a Doppler effect.
I think that's backwards.
Backwards?
Yeah. The frequency was getting higher, and as it goes by you, it'll become lower.
Right. So the physics of that is that the train is giving off sound waves. But if you're here listening, the train is moving as it blows its whistle, then these sound waves get scrunched up and they get closer together. As the train passes you, and you're back here, the sound waves get further apart. So the frequency changes. So you hear the Doppler effect. You hear the train coming toward you, then receding. Well, it's the same with stars. The universe is expanding, and when you look at that red line of hydrogen, you see the same pattern. So you know it's hydrogen coming from that star, that galaxy, but they're all shifted. They're shifted because of the Doppler effect, because the star is moving. And that's how we've realized since the 1940s that the universe is expanding. When you look in every direction, all galaxies are moving away. They're all Doppler shifted in one direction. And so you know the universe is expanding without question. That's how you know it, because of the fingerprint of hydrogen. Anyway, that's how Bohr proved that his atomic monoatom was right, because he could then explain by the space of these orbits, he could calculate them, he could explain the wavelengths of these emitted lines when hydrogen is excited, electrons jump from one to another. Huge success. That's why Bohr got the Nobel Prize. Chadwick worked in Rutherford's lab. Chadwick was British. He first worked in Berlin with Geiger, and at one point he worked with Geiger, and in World War I then, while he was in Germany working with Geiger, Hans Geiger in Berlin, Geiger kind of thing, he was interned in a prisoner of war camp outside Berlin. And luckily he didn't get killed on the front lines, but he got captured. So he spent his time in the war years working on, he set up his own laboratory in the stables in Berlin of a prisoner of war camp. And he started working on ionization of phosphorus. And Geiger then saw how important Chadwick's work was. So Chadwick got him out of the prisoner of war camp, got him back to his laboratory so he could work on these physics experiments. After the war, he went to work with Rutherford. See, Rutherford had the idea that there was something else in that little small nucleus besides a positively charged proton. And the problem is, if you have a nucleus with a whole bunch of protons, they're going to repel each other. There's a nuclear force that no one understood that held things together, but there also was the electric force, and there's electrical repulsion. So all those protons would be pushing each other apart by the electrical repulsion. And Rutherford knew that was a stability problem, so Rutherford expected that there must be a neutral particle in the nucleus that provides the nuclear glue, something that experiences the nuclear force along with the proton but which had no electrical charge. That was a suspicion of Rutherford's. So when Chadwick joined his laboratory, he set about doing experiment of taking alpha particles from something radioactive like radium or polonium, hitting a thing full of beryllium, because they knew that when alpha particles hit beryllium, you made something. You made something that was very penetrating. Marie Curie's daughter and her husband, working in France at the Radium Institute, felt that you were making gamma rays when alpha particles hit beryllium. Whatever this penetrating stuff was, even more paraffin for gamma rays, higher energy X-rays. Rutherford didn't believe that. Chadwick didn't believe that, so his job was to explore what these things were. He then did an experiment. He looked simple, but was not. He hit this mystery radiation, hit paraffin. You then make protons that you couldn't exactly count with this newly found, newly constructed Geiger counter that would count how many protons there. And that proved that there was a neutral particle here. It was neutral because it didn't deflect, didn't have a charge, but the electric field couldn't bend. It had to be massive, like that of a proton, because a little electron or something couldn't eject protons into paraffin. And so by detecting these protons and doing some calculations, he realized that the mystery particle people have been searching for is a neutron. And that was verified Rutherford's gut feeling of 10 years earlier, 20 years earlier. So finally in 1932, Chadwick, working in Rutherford's lab, published the discovery of the neutron. And that meant that the nucleus of helium has 2 protons, 2 neutrons. Hydrogen, element number 1, can exist in this stage as normal hydrogen, or hydrogen called deuterium can exist with a proton and a neutron in the nucleus, electrons moving around it. There does exist tritium with a 12-year half-life. It can have 2 neutrons in the nucleus. Helium can exist with 1 neutron or 2 neutrons. This was stable. So that meant that there were different possibilities for different kinds of nuclei. We now call these isotopes of hydrogen, isotopes of helium, because the number of protons is the same, but the number of neutrons is different for these different isotopes. So then everything started to fall in place in 1932, the discovery of the neutron by Chadwick. And then it was only 11 years later before people in Oak Ridge built the first reactor based upon knowing what the neutron is and using it to make uranium fission.